Curve has equation y equals x to the power of 5 minus 2x squared plus 9. The point P with coordinates minus 1, 6 lies on the curve. Now let's look at part A. Find the equation of the tangent to the curve at the point P, giving your answer in the form y equals mx plus c. So it's mentioning a tangent. Let's first of all recap what a tangent is. If you have a curve, a tangent is a straight line that touches the curve at one point. So for example, if we plot 1 point on the curve, this red dot here, a straight line would touch the curve at that particular point, and that would be the tangent to that curve. Just for extra information, if you then have a perpendicular line to the tangent going through the same points, and we call that the normal to the curve at that particular point. Now this question isn't asking about the normal, it is asking about the tangent. Now if we want to work out an equation of a tangent, we're talking therefore about an equation of a straight line. Now to work out an equation of a straight line, there are two things that would be useful to know. A point on the line, which we know minus 1, 6, and the gradient of the line, which we don't know. But what we do know is the equation of the curve. Now, if we differentiate the equation of the curve, this would then give us a formula for the gradient of the curve at any point. Now, the gradient of the curve does mean the gradient of the tangent at any point. Therefore, we need to differentiate the equation of the curve. Now, let's quickly recap how we differentiate. If you have y equals x to the power of n, say, then the differentiation, we would bring the power to the front, so it would become nx, and then we would decrease the power by 1. So 1 less than n would be n minus 1. So let's go back to the equation. We have x to the power of 5. If I bring the 5 to the front and decrease the power by 1, we would have 5x to the power of 4. The second term at the moment is minus 2x squared. If we differentiate that, the 2 would come to the front, which would make it minus 4x, and 1 less than 2 would be 1. So we write down minus 4x. Then the differentiation of plus 9 is 0. The differentiation of any constant is always 0. So the differentiation is 5x to the power of 4 minus 4x. This therefore is a formula for the gradient of the tangent at any point. Now we're not talking about any point, we're talking about one point in particular. We're talking about minus 1, 6. So we need to know what is the gradient when x is minus 1. So if we substitute that value into the differentiation, it would give us the value of the gradient at that particular point. So instead of x, we're going to write down minus 1. So we have 5 times minus 1 to the power of 4, minus 4 times minus 1. And that gives us 9. Now if that's the value of the differentiation when x is equal to minus 1, that means that 9 is the gradient of the curve when x is minus 1, which therefore follows that the gradient of the tangent when x is minus 1 is 9. So we now have 9 for the gradient of the tangent, and we have our point minus 1, 6. Those are the two important things that will help you work out an equation of a straight line. Now, an equation of a straight line, if we substitute those values, so our coordinates minus 1, 6, and the gradients of the tangent 9 into a general format for a straight line equation, we would get y minus 6 equals 9, and then if I open the brackets, x minus the x value, which is minus 1, and close the brackets. If I multiply out the brackets, we would get y minus 6 equals 9x plus 9. So that's the equation of the tangent. Going back to the question, it did actually say, though, to write the equation in the form y equals mx plus c. Now, we're almost there. What we want to do is just add 6 to both sides. And if I add 6 to the left side, we would end up with y. And if we add 6 to the right side, we would have 9x plus 15. So that now is of the right format. The equation of the tangent is y equals 9x plus 15. Now let's have a look at part B. The point Q with coordinates 2, k lies on the curve. find the value of k. If 2k lies on the curve, then what that means is that when x is 2 and y is equal to k are substituted into the equation, they will satisfy it. So it would mean that basically the equation would be true. So what we need to do is substitute x equals 2 and y equals k into the equation. So for every y, we change it to be a k, and for every x, we change it to be a 2. So we end up with k equals 2 to the power of 5 minus 2 times 2 squared plus 9. Simplifying that in stages, we would get k equals 32 minus 8 plus 9, which would leave us with k equals 33. So the coordinates of Q are 2, 33. If we now have a look at the second part of part B, verify that Q also lies on the tangent to the curve at the point P. Now remember in part A, we did work out the equation of the tangent. The equation of the tangent was y equals 9x plus 15. Now, if Q also lies on the tangent, it would mean when we substitute x equals to 2 and y equals to 33 into the equation of tangent, then it would be true. So the point satisfies the equation. So for every x, we change it to be a 2, and for every y, we change it to be a 33. So what we know is true is that 33 must be equal 9 times 2 plus 15. 9 times 2 is equal to 18. 18 plus 15 is equal to 33. As both sides are equal, it means that the values do satisfy the equation, which means that Q must also lie on the tangent. Let's move on to part C. The curve and the tangent to the curve at P is sketched below. The first part of this question is saying find, and we have an integration of x to the power of 5 minus 2x squared plus 9, and we can see that we have limits 2 and minus 1. This is therefore a definite integral as we have limits, and what this means is we need the value of the integration between 2 and minus 1. So the first thing we need to do is to actually integrate. So remember with integration, we increase the power by 1 and we divide by that power. So if we have a look first of all at x to the power of 5, that would become x to the power of 6 over 6. The second term minus 2x squared, if we increase the power by 1, it would become minus 2x cubed over 3. And then the last term, anytime you integrate a constant, you just add an x to it to the end. So plus 9 becomes plus 9x. And we have our limits 2 and minus 1. If we substitute 2 in, we would get 2 to the power of 6 over 6 minus 2 times 2 cubed over 3 plus 9 times 2. We also need to substitute minus 1 in and subtract this away from our answer to when we substitute 2 in. So I'm going to write down minus, and then in brackets we have the minus 1 power of 6 over 6 minus 2 times minus 1 cubed over 3 plus 9 times minus 1. Even though you can type all this in one go in a calculator, it's sensible to work it out in stages to show your workings out, show every step in case you slip up somewhere so that you do get your method marks then as well, and that you're aware at the end if your answer actually does make sense or not. So if we work it out in stages, we have 2 to the power of 6 over 6, which gives us 64 over 6, next term minus 16 over 3, and then we've got the plus 18. The second bracket then would leave us with 1 over 6 minus 2 over 3 minus 9. If we simplify each bracket, we end up with 70 over 3 in the first one and minus 49 over 6 in the second, which means we have in the end 70 over 3 plus 49 over 6, which leaves us with 189 over 6, or if you prefer, you can write this as 31.5. So that's the Now let's look at the second part. Hence, find the area of the shaded region bounded by the curve and the tangent to the curve at P. Now let's first of all go back to our different parts of this question to see what we already know. From part 1 and part C, we do know the value of the integration between minus 1 and 2 is 31.5. We know as well from our parts A and B that Q is 233. and P is -1, 6. And P and Q are both points on the curve and tangent as established in questions A and B. So that's the information that's given to us, and it's useful to add that onto the diagram. Now, if we have a look at the information that's given to us and have a look at the diagram, we can work out that the shaded area would be the area of this particular trapezium. If we can work out the area of that trapezium, if we can then work out the area under the curve between the limits of x equals -1, x equals 2, and take that away, it would leave us with the shaded area that's in the question. So that's what we need to do. We need to work out the area of the trapezium and we need to work out the area under the curve. The area of the trapezium, first of all, remember from your GCSE work you were given this formula, but now we do have to learn this. It is half brackets a plus b times h. A and b represent the two parallel sides and h is the horizontal distance, in this case, between those parallel sides. So you can see that the two parallel sides are highlighted. We need to know what they are. We can see that A, if you like, we'll label that one as the first one, would be 6, as it would be the y ordinates of P. And we can see that the second line, the value of B would be 33, as it's the y ordinates of Q. And then h would be the distance between those two parallel lines, and we can see that's 3 units, from -1 to 2. So we substitute those values in. We have half times 6 plus 33 multiplied by 3, and that gives us an area of 58.5. Now, for the area under the curve, we would normally need to integrate the curve, and we would need to work out that the value of integration between x equals -1 and x equals 2. However, we've already done that in part 1, so we can use that answer to help us here. We know that the value of integration is 31.5. Therefore, the shaded area that's in the question would be 58.5 minus 31.5. So that gives us a final answer of
27.
Seen the derivation of the area of a trapezium before, and there are different ways of doing it. This is quite a nice way. So we can see we have a trapezium here, base is A, the lid, if you like, is B, and the height of it is H. So the first thing we do is we make another trapezium by rotating this one round. So that gives us a parallelogram. You perhaps have to do a little bit of work to prove that this side and this side are parallel, but it's not too difficult. And we can now put the labels on for those sides. And now we can see that we have the top and bottom of the parallelogram length is A plus B, or A plus B. So the next thing we do is we slide this triangle here along to the other end. So we keep the area of the whole object the same, we slide that along. But we slide that along. So now we can see we have a rectangle. The area of this rectangle is the base, which is A plus B, times the height, which is H, and that gives us H times A plus B. And then, of course, the trapezium is half that, so that gives us our final formula for the area of a trapezium, which is half of H times A plus B.
In this question, we'd already found the area under the curve, and so it was natural to use the formula for the area of a trapezium to work that out. But of course we could integrate the line from the -1 up to the 2 just as well. And actually, had this been a question where they just asked you for the shaded area without first asking you to work out the area under the curve, then, as you may know, you could, instead of doing the bits separately, you could combine them as one integral. And what that would look like is that we would be integrating between -1 and 2, and we would be doing the line take away the curve. And then we could put the formulae in that we've been given. So that's just to mention that sometimes with these integration questions, it's just as easy to make one integral, generally involving subtraction, occasionally addition, and then to work that out. Wouldn't be appropriate in this question because of the way that the question is structured. What you might find interesting is to see how we can get the formula for the area of a trapezium through integration. So, if we make a little sketch, if we drop lines down here and here, then the area in there is that of a trapezium. These have been dropped down at right angles, obviously. And then we might call this point x1 and this x2, this one y1, this one y2. And then the lengths on this diagram, that would be our A, that would be our B, and the distance between x1 and x2 would be our h. And we're also going to say that the line is y equals mx plus c, as is traditional. So what do we know? Well, we know that the point here and here, the points are on the line, and so that means we have that y1 equals mx1 plus c, and y2 equals mx2 plus c. We can see reasonably clearly that h is going to be the value of x2 take away x1. We can see that a is equal to y1 and b is equal to y2. So now we can have a look at our integral. So the area of the trapezium, call it A as we have on the diagram, is the integral between x1 and x2 for the function y, and that is the same as saying x1 to x2 of mx plus c dx. So that gives us m x squared over 2 plus cx between x1 and x2. Now I always put brackets ready to pop everything into. It takes care of that worry about the minus sign in the middle. So we have m x2 squared over 2 plus cx2 take away mx1 squared over 2 plus cx1. Incidentally, as I dribble on writing all this down, you could have a try of it yourself. All the information's there for you to end up with the formula. So if you want to pause and have a go and then have a look through the rest of the video, that would be good practice. Okay, now we can see that we've got two terms with m over 2 involved. So what I would be tempted to do here, what I'm going to do, is to take those out, and you'll see a familiar difference of two squares popping up, and then we've got our c times the x2 minus the x1. Okay, so this gives us m over 2 times x2 plus x1 times x2 minus x1 plus our c times x2 minus x1. And we can see in both of those bits we've got that. So we can take the x2 minus x1 out as a common factor, which will give us m over 2 times x2 plus x1 plus the c, they're both times by x2 minus x1. And now we can take a half out. Got to be a little bit careful, because whilst that leaves us with m times x2 plus x1, we must remember to say that we now have two lots of c. There's our x2 minus x1. And now we split this bracket here up into mx2 plus c plus mx1 plus c. And then, hey presto, we have mx2 plus c and mx1 plus c are both up here. So this becomes, for the second half, this one we have y1, and for the other bit we have y2 times x2 minus x1, and then we know that y1 and y2 are actually a and b. x2 minus x1 is actually 8, so this gives us a half of a plus b times h, which is what we would expect. So, nice little bit of maths for those of you who like it.